Okay there, rock stars. Let's get rocking and let's talk some similarity. So this is a concept that, and I don't want to mince words here, that it's probably the most important concept we study in geometry. The whole first semester we talked, congruency. We talked proof, and that was all really to get us ready to start formulating some very serious arguments this semester. And I think you guys already experienced in the last couple of classes that the difficulty of this class has just increased pretty significantly. So you're here because you want to make sure you have all the information you need to proceed forward. Thank you for that. Let's get talking about similarity. So you probably want to pause the video, maybe you can catch up with me. And what I'm going to be doing is bouncing back and forth between this Cornell note sheet and then some scratch sheets, so we can kind of make sure we have a really good sense of what is going on. All right. So without further ado, let's talk about how you prove two objects are similar. So you spent the last couple, well, 4 class periods just kind of diving into this whole world of similarity. And hopefully what's come out of it is a working idea of how this new transformation, this new concept is different than congruency. But let's put some formality to it. So right off the bat, let's talk about some of the essential vocabulary you need to actually understand uh, the concept of similarity. And let's start with the definition of corresponding. So corresponding is not something that's new to us. It's actually something we handled last semester. But corresponding just refers to like two things that are in the same general position. And let me go ahead and write that out. You might want to fast forward a few seconds, but this simply refers, let's see, I already got one F? Yeah. Okay. So let's talk about what this actually means. So let me flip over to a different program. This is just paper. And if I'm talking about objects in the same general position, I think like a good example for this idea of corresponding would be to go back to the world of congruency. So let's say I have these two triangles. Let's say triangle A, and I'm comparing it to triangle B. Okay. If I were to label these two triangles A and B, let's just label some angles 1, 2, 3, 4, 5, 6. Of course, you don't have to write this down; just kind of pay attention. And then let's see, X, Y, Z. Let's name some vertices. W, V, U. Now, if I asked you for some corresponding pieces, and let's say I was looking at X, Y, hopefully you respond the corresponding side in triangle B would be WV. So XY is going to correspond to WV. Okay? And I'm simply saying that because they're located in the same general position in both triangle A and triangle B. Kind of in the same sense that if I want you to name like the angle is corresponding to angle 1, certainly hopefully you'd respond angle 4 is corresponding. So again, that's what I mean by this idea of the same general location. Um, and it doesn't necessarily mean that they're congruent, doesn't necessarily mean that they're not. It's just simply naming and identifying a location, which is something that we maybe want to make a special note here, that when you talk about corresponding, it's all about location. So this only speaks to location. Okay? So being corresponding does not guarantee congruency. It does not guarantee non-congruency or any relationship of the sort. Again, it's simply a position. Now let's talk ratio. Okay? So when we're talking ratio, what we're really talking about is a comparison of two objects. Now, what was in particular to note about a ratio is not just a comparison of two objects, but really it's about comparing measures. Okay? And these measures don't necessarily have to be numerical, they typically are. And I'm not going to go delve too kind of deeply into this because we talked about it in class over and over again. But again, the thing to note here is the comparison doesn't have to make sense. You just have to make it because I'm asking you to make it. So like for example, and just some really quick ones, like 1/2 is a ratio that compares 1 of something to 2 of something. That could be like 1 rabbit to 2 dogs. That could be like 1 light bulb to 2 elephants. It doesn't really matter. It's simply a ratio because I'm asking to compare it. The fraction version of this by far is probably the most useful, but don't forget there's also alternative versions like 0.5. We can go 1 to 2 in column notation, and of course just verbally like 1 is to 2. And I'm leaving those as general numerics, but again, we can always tie a word to it like 1 apple to 2 oranges or what have you. Okay? Proportional might be a new one now. This is in the other video that's being posted here as well, but I just want to reinforce it. When we talk about a proportion or talking about proportional, this just refers to multiple objects holding the same ratio. Okay, so let's write that down. Okay, so this actually reveals some really important information. The main thing being this idea of same, because same implies equality. So another way to look at this is if you are proportional, what you're actually exuding is equivalent ratios. So kind of put it in parentheses here is just like a parenthetical. What we're really talking about here is equivalent ratios. Okay. Now this is going to play out kind of some very interesting ways. And I'm going to flip back to paper here so we can maybe get a sense of it. Come on, paper, turn the page for me. How do I do that? 2 fingers? Oh, maybe this. Okay. Okay, so when you talk about proportional and proportional thinking, the way this is going to play out for us is to look at not proportional, T-I-O-N-A-L. Okay, whatever. When you talk about proportional, you can look across like multiple objects. So what I mean is kind of like this. Let's say I have this object, and let's say it's 1, 2, 1, 2, and then I have this big object over here, and let's say I'm just going to, for the sake of argument, triple all the side lengths. So that's going to be 3, 6, 3, 6. Now we can claim this is proportional simply because if you look at any of the combinations of ratios, they turn out to be the same. So if I look at this one, 1 to 3, and then I look at the top one, 2 and 6, we can actually claim they're proportional simply because those are indeed the same ratio. Same thing with this, again, we're reverting back to 1 and 3, and now we're back to 2 and 6. Proportionality comes from the fact that this is actually all going to be the same ratio, even if they're written numerically different. Of course, you can test this if you don't believe me. Look at each of these individual fractions. You realize they all... I'll get out of your pen. Oh, okay, there we go. We can say that these all are going to revert down to 0.3 repeating, confirming that all the ratios of corresponding side lengths were indeed... Oh, yay, Battle Beach. Womp. Okay. That all the ratios of corresponding side lengths were in the same ratio, ergo that it's going to be proportional. And that's what I mean by proportional. Now that's going to be a pretty important concept for us when we talk about similarity. In fact, it's the concept when talking about similarity. But let us move on to the next item of business. So let's talk about the next big question we have to answer in these notes. And that has to do with trying to figure out this idea of proportional. So kind of like a leading question here. We need to figure out how dilations actually tell us exactly what the definition of proportionality is. So here it goes. Oops. All right. So to understand how definitions will actually help inform what similarity actually is, let's go ahead and quickly perform a dilation. Now, if you don't know what dilation is, you probably want to maybe watch the other video first, maybe review your notes. But dilation is just this new non-rigid transformation that we've been dealing with, and it's really supposed to be on a coordinate grid. Okay? And for our purposes, for our example, I'm going to just put in a really quick coordinate grid here. You guys can do the same. I'm just going to keep it in the first quadrant. So to perform a dilation, you actually just need a few things. You need a center, and for our purposes, we're going to kind of generically pick the middle to be our center, or sorry, origin to be our center. You need some points, so I'm going to pick just a few here. I'll pick point A, I'll pick point B, and let's pick point C right here, which will form for us a triangle. Now, in terms of actually performing dilation, if I take this center, ooh, whoa, 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 notes, get back under control. If I have to take the center here and extend the line through A, and extend the line through C, and extend the line through B, that will tell us precisely where our image is. Let's go blue. So A is going to move along this line of dilation from the center, which I'm just going to call the origin, called O, and find a new location at A prime. B is going to do the same, and then of course C is going to do the same roughly right here. Okay? And what's left is our new image triangle. So that in essence is what a dilation actually is. And I think if we understand that this is how dilation is performed, we simply move A to our new location along the line dilation to A prime, C moves up to C prime, and B moves up to B prime. We're going to be in good position to understand how this works when we're not on a grid. So what do I mean by that? Well, let's figure this out. I know for a fact that A has to move up A prime, C up C prime, B up B prime, and that's going to be by same consistent ratio as the side lengths. So what I mean by that, if like, and I'm just making these numbers up, but please don't take this too seriously, just for concept. But if that's a distance of 2 here, that's going to be a distance of 4, which that means if I look at this distance, and let's just say for sake of argument it's 3, that means this distance has to be 6 in the same ratio. So if you think about what what's actually does for us, like moving these points using the consistent ratio value, what it's actually going to do is ensure that AC is going to be in a similar proportion with A prime C prime. So again, this is just for example. Let's say this side is now 4. That means it's going to guarantee this is 8. If that's 1, it'll guarantee this is 2. So through a dilation, through understanding that you're moving along these dilation lines, what that's going to do, if for one part, is to ensure that all the sides of the pre-image and image are proportional. All right. Now the second thing you guys noticed, and you guys did a good job of this in class, is to point out that because we're trying to maintain the same shape and just make it bigger or smaller, these lines, A, B, and say A prime, B prime, turn out to be parallel. Same is true here. And then, of course, this guy right here. So this is really important because, of course, if they weren't parallel, you'd no longer actually have the same shape, just simply a different size. But the offshoot from this is that it also guarantees that these angles are going to be congruent. Because if the lines weren't all consistently parallel, then the angles themselves wouldn't be congruent, which is the other kind of general outcome of performing a dilation, is that parallel lines inform or create congruent angles. Okay? So if you think about dilation, you think about these two things. Keeping the same shape and making it different size ensures us that all the side lengths will be of the same ratio, the same factor, bigger or smaller. And then the parallel lines, because we want to keep the same orientation, the same shape, but just make it a different size, is going to force us to have congruent angles. So those two together are going to form our definition of similarity. So allow us to write our next question, which is, what is the definition of similarity? Okay, And really this turns out to be like the big question, the biggest question. But since dilations are a form of similarity, and we just did a good job in the previous question vetting it out, we actually have a nice two-part definition for similarity. So, objects are similar. If and only if two things are true. All corresponding angles okay? So all corresponding angles are congruent, which we actually got from the pink condition above. And then the second thing is that all corresponding sides are proportional. Okay, so how this kind of looks, I can give you kind of a quick example. So forget about dilations, forget about the grid. The best example I can give you is let's kind of pretend that you have this triangle here. Um, let's call it like A, B, C, and let's label these 1, 2, 3. And then you have this other triangle somewhere else, not on a grid. Let's call it D, E, F, because it's not a dilation, therefore it should be no prime notation. And let's just say angle 4, 5, and 6. If these two triangles are similar, here's what has to be true. Angle 1 has to be congruent to angle 4. Angle 2 congruent to angle 5. Angle 3 congruent to angle 6. And that takes care of the angle definition. But also, all sides are proportional, which means they share a ratio. So what I mean is, if I take the ratio of AB, which is on the left, and compare it with the ratio of DE on the right, that has to be in the same proportion as BC, as BC is to EF, excuse me, and of course AC along the bottom is to DF. So this part right here is a congruent triangle or congruent angles part, and this part is a proportional. Okay? Don't get confused on this part on the right. I'm simply saying if I had the side length, I can put them into a divisional ratio. Okay? So just quickly wrapping up, and I know it's kind of getting long, and I apologize for that. Just a couple quick things to kind of note about similarity, some kind of special things. The one thing I want you to note is what is the standard naming convention for similarity? Wow, wow, Mr. Collins. Okay, naming. Okay, so the naming convention of similarity is if you have two triangles that are similar, and let's just say again, let's just bring up triangle ABC and triangle DEF. The standard naming convention is just like congruency. The order here does actually matter, but we use a new symbol. So the standard naming convention is to name your triangle, in this case ABC. Over here, name it in the same order as in terms of your corresponding side lengths. So this will be triangle DEF. And then instead of using the congruency symbol, we're going to use a single tilde mark. That is a naming convention that I'm going to expect you guys to use while in class. All right, so that is similarity. Now, there's going to be, leave a little space here at the bottom. If you're copying along with me, you should have plenty of space here. Because below we can add some stuff later on, especially after you guys get a little more experience with proportionality. But there you guys have it, similarity. If you kind of understand the dilation, how it just kind of blows up an object or shrinks it, we can extract two main qualities. One being that the parallel lines, because you're trying to keep the shape oriented along these dilation lines, creates parallel lines. And the second thing is, since you're just trying to make it bigger or smaller, the consistent ratios will force the line segments to be proportional, which is actually our definition. If things are similar, you know they have to have all corresponding angles that are congruent, and all corresponding side lengths are proportional, as demonstrated by this picture. And using that naming convention, you guys should be good. So one last thing to wrap this up. The last thing I need you to do is to reread the notes and highlight 5 words or phrases essential to the essential question. and highlight them, of course. And I need you to craft a summary in this space that uses that answers the essential question, but uses the words or phrases you highlighted. And then, of course, post your summary in Edmodo, and you get some Class Dojo points. That's all I got for you guys. Pretty long video, and I apologize for that. But hey, it's a big concept. It's going to take some time to vet out. There you go.